Uh, okay, so I gave a bunch of problems. So this is the problem set which I handed out. Um, yeah. Um, so let's look at number 12. Okay, so number 12 throws a little bit of a twist on the Bikhchandani model. Um, so you have to be careful how to solve it. So what is this saying? This creates an asymmetry, this question. Uh, so you have the standard model, right? There's a sequence of investors, each gets a noisy private signal. Um, but the asset returns, in the good state, it's +1, and in the bad state, it's -2, right? So now we have broken the symmetry there. The priors are equal. Accuracy of the signal is 3/5, right? So 2/5 chance it will be wrong. And you have to basically analyze the model, nail the numbers. After what kind of histories will an information cascade start? Calculate the probability of the right and wrong cascades in the long run. Okay. Now the solution, let me pull up the solution here. Number 12. Okay. Here. Um, so now the first question to ask is, how high does the posterior belief have to be for an investor to want to invest? Yes, and that's no longer half, right? In our original analysis that we did in class, it was half because the payoffs were +1, -1, right? And you started with a prior of half. Everything was very symmetric. So all you needed was an assurance that the state is good, is more likely to be good than that. Now, here, whatever your posterior is, let's call it lambda. So if you believe with probability lambda, it's a good state, your expected payoff is lambda times 1 and 1 minus lambda times -2. So when is this positive? This is positive when lambda is greater than 2/3. So the threshold of investment has moved up from half to 2/3. Right? That's the first thing to note. Next, let's calculate that if all the signals were pooled together, we knew we had access to a whole sample of signals. How many net positive signals will it take to push the posterior above this magical threshold of 2/3? Okay. How many extra good signals are needed for an investor to want to invest? That's the next question. And starting from a prior of half. So we have done this calculation before, right? Everything depends on net signals. It doesn't depend on how many positive signals you have, how many negative, but what is the difference? So let's say there are k net positive signals, right? K more positive signals than negative signals. So then, this is Bayes updating. Yes. Again, we have done this before. The formula is p to the power k divided by p to the power k plus 1 minus p to the power k. Now, we are given very helpfully the value of p. So we can just plug in numbers and just check that investment is optimal if and only if k is 2 or more. Okay. In the symmetric Bikhchandani model that we did in class, all that was needed is that k is greater than or equal to 0. And if it's even 1, then investment was optimal. But now you need at least 2 net positive signals to want to invest. Um, okay. Now, in this case, the answer turns out to be quite boring. Yes. Even the first guy will not invest. So you have a essentially information shut down right from the start. Yes, even if the first guy gets a positive signal, his revised belief that this is a good stock will rise to 3/5. That's 60%. And he needs a 67% threshold to want to invest. So regardless of his signal, he won't invest, and anyone coming subsequently learns nothing from the first guy's decision. And so you have like a null kind of cascade starting right from the start. So that's not very interesting. But so in the solution, I go on to sketch out another value.
Sir,
Yes.
sir, why is the probability of being wrong is half? It should be 1 minus p, na? Like 2 by whatever the value is. 2 by 5.
Why is the probability of
It being wrong is half. A cascade start immediately given the parameters of the problem, and then it is written the probability of it being wrong is half.
oh, I see, I see. Because see, the prior is half and half, right?
Sir.
So we're calculating the probability of a round cascade even before a single signal is actually realized. We're at the very beginning, remember? Yes. Now, when we look at the game, we find that the first guy will stay away from investment, and so will everybody else. So a non-investment cascade will form right from the start. Now, what is the probability that this decision is wrong? Well, this decision will be wrong whenever the state is actually good, which has a probability half.
Okay, sir.
I think what you're thinking about, I can see where you're puzzled. You're trying to calculate the probability that the cascade is wrong after taking into account that the first guy got a good signal.
Mm. Yes, sir. Like I was thinking in that
Yeah.
way.
No. So that calculator will be right. In that case, it will be 2/5, right? But we are calculating it even one step before that.
Okay, sir. Thank you, sir.
Yeah. All right. So let's work with a different value, which makes for some action going and some interesting calculations. Okay. So P equal to 4/5. So now um, investment is optimal for K1 or higher, and not investing is optimal for uh, any K which is 0 or less, right? So if K is 0, that means the posterior is half, and half is less than 2/3. So not investing is optimal. And if K is even 1, then after base updating, the posterior rises to 4/5, which is 80%, which is higher than the investment threshold, 2/3, right? Um, um, okay. Um, so, um, so this is some notation we are introducing, right? What is Q0 theta? Um, Q0 theta is the state, the true state, right? Uh, and if we have 0 net positive signals in the public domain, okay? So given the history so far, suppose it has been learned that there are zero net positive signals. So in that case, the eventual probability of a cascade is, let's say, uh, not the eventual, in the next round, the probability of a cascade is Q0 of theta, right? And similarly, Q1 of theta. So obviously, when the number of, so all the action will be when the net positive signals in the public domain is either 0 or 1. Okay. If it ever gets to 2 or -1, then a cascade will have already started. So that's why we are focusing on 0 and 1. Okay. So now we can write down two sort of equations which connect these probabilities, right? And that'll help us solve it. So let's understand these equations. So suppose the true state is 1, okay? And so far, the number of net positive signals is 0, okay? So that's the subscript here. Now, another investor, another signal comes forth, okay? Now, the true state is 1, okay? So with 4/5 probability, the new signal will be a positive signal, right? So the number of net positive signals will go up to 1. Okay. So when there are 0 net positive signals in the public domain, this is the potential. This is the long run probability of a cascade, right? One more investor and signal comes forth. With 4/5, that guy will get a positive signal. He'll invest, and so the system will move to a new state where the probability depends on one net positive signal being out there, right? So with 4/5 probability, that'll happen. With 1/5 probability, what will happen is this guy, unfortunately, the new guy, will get a negative signal, right? And the moment that happens, the number of net positive signals will drop to -1. And the moment it goes to -1, and a non-investment cascade starts, right? So the probability of an investment cascade collapses to 0. So starting from 0 negative signals, either one more positive signal and one more investment comes forth, in which case the probability translates to, transitions to this, or one negative signal comes forth, probability 1/5, in which case the investment cascade just vaporizes, right? It will never happen. A non-investment cascade starts. Now, what about Q1? Suppose right now the number of net positive signals is 1. Okay, so that's why this probability applies. Now, starting from that situation, what if one more positive signal comes? So the next investor gets a positive signal, invests. So now in the public domain, there are +2 number of positive signals. Okay. And so the probability of an investment cascade jumps to 1. And that happens with 4/5 probability. With 1/5 probability, what will happen is that the new guy gets a negative signal, right? So now the number of net positive signals drops from 1 to 0. And so now the probability that will apply is this Q01. Okay, so let me draw a picture to try and make that a little clearer. I'll have to just give me a second. All right. So we have this line, which is probability on good state, right? Probability of the state returns being +1. Now, in our first calculation, we saw that there are these notches. Okay. In fact, I should use a different color. So this is 0, this is -1, this is -2, this is 1, 2, etc. So an investor, after taking into account all information, if the net number of high signals, positive signals he has is 0 or any less, then he will choose non-investment. And for these values, he will choose investment. Okay. Now, at any point, if the number of known positive signals hits 2, right, then an investment cascade will start. Because if the next investor, even if he gets a negative signal, the net number will fall from 2 to 1, and he still wants to invest, right? So from 2 onwards, you have a cascade on investment, right? And from -1 onwards, if it ever becomes -1, then even if he gets a positive signal, he's still in the red zone, right? He still wants to non-invest. So over here, you have a cascade on non-investment, right? So the only 2 values for which a cascade is yet to start are 0 and 1. If the based on current history, if the net positive signals is either 0 or 1, then things are still up in the air. A cascade hasn't started, right? It will depend on the signal of the next guy. So in our analysis, then we say that, okay, let's focus on these 2, right? And let's say that if so these things are called state variables. So this is a stochastic process. Yes. So these are state variables. So the state variable, which is the net number of positive signals or high signals so far, if it's either 0 or 1, the game is still on, right? So we'll say that at this point, if it's 0, the probability of ending up here, an investment cascade eventually, is Q0. And today, if you're sitting on 1 net positive signal, then the probability of ending up here is Q1. Okay. And of course, 1 minus Q0 is the probability going into the opposite cascade, and similarly 1 minus Q1. Now, we have to do this analysis. We have to do the same thing for the 2 possible values of the state. So let's say if the true state is return is +1, then these are the probabilities. Okay. I think, let me not write the plus. This looks cumbersome. Anyway, okay. Now, how do we calculate the values of Q0, Q1? To calculate that, we will have to recognize that there is a relationship between Q0 and Q1. Yes. And once we write down that relationship, then we'll be able to solve it. So the relationship is like this. So suppose we start here. This is the state variable, 0, right? Number of net positive signals is 0. Okay. Now, what happens when another investor comes forward? Well, with 4/5 probability, the next guy will get a positive signal because the state is, good. So with 4/5 probability, we'll jump from here to there next period. And over here, the probability of an investment cascade eventually forming is Q1 of 1, right? Now, with 1/5 probability, the jump will be in the other direction, that the next guy gets the wrong signal, and so the number of net positive signal becomes -1. And once it becomes -1, as I said, a non-investment cascade has started, so the probability will ever get investment again is 0, right? And this exactly is Q0 of 1. Next period with 4/5 chance will go here, and then there's a probability of moving into this cascade, and with probability 1/5 will slip into the other cascade. So this is one equation. Now, similarly, you can write another equation which relates the probability at 1 to the probability at 0. So how does that go? Well, suppose there's one net positive signal. So starting from here, another investor comes, gets a signal. Suppose that signal is positive, right? So with 4/5 probability, that will trigger an investment cascade. Okay, so we'll have investment with probability 1. And with 1/5 probability, will slip down to 0 again because the new guy's signal will be negative. So it'll nullify the one net positive signal that existed before. So then the probability of getting investment again is going to be this. So this is Q1. So now we have two simultaneous equations in two unknowns, okay, Q0 and Q1. And by solving them, we can find the values. Yes. So now that'll give us Q01, Q11. Now, what if the state, this is for, where those who are calculating the probability, we standing outside, we know that the state is, it's a good state. What if the state is -2? Well, there the probabilities are Q0 of -2 and Q1 of -2. Okay, they'll take different values, but we can follow the same method to calculate all of that, right? Because suppose the true state is bad and the net number of signals is 0. Well, with only 1/5 probability, the new guy will get a positive signal. So with only 1/5 probability, we'll move to Q1 in the state of -2. And with probability 4/5, the new guy will get a negative signal, which means a non-investment cascade will be triggered. Starting from 0, we slip into the red zone deeper. So here, this is 0. So basically, it's the same kind of simultaneous equations, except that these probability weights are flipped around because the state is now different. Sorry, this is 1 and 4/5 Q1. 0 at -2. So that will give us the other pair of probabilities, right? Q0 and Q1 when the actual state is -2. So that's how you calculate it. Yeah. And eventually you may want to, depending on the question, if the question says that what is the so here, when the true state is positive, these are the probabilities of the correct cascade starting. And when the true state is -2, these are the probabilities of the wrong cascade starting. So if you're interested in the probability of the correct cascade, in this case, which is the cascade of non-investment, then you have to focus on 1 minus Q0 and 1 minus Q1. Yes. Okay. So that's a roundabout. You can see that how fragile these models are. There's a little bit of twist or asymmetry. You have to work much harder to solve it. Yes.
Sir,
Yes.
sir, in the first equation, with the 1/5 probability, why are we writing 0? Why not 1 minus my Q naught of 1?
Because, okay, there are many things flying around. All right. So you have to be very, very careful about every detail. The stuff inside bracket is the true state. Okay. Having noted that, let me set that aside. Right. All of here we are just calculating, taking into account that actually the state is good. Okay. Fine. Every number relates to that. Now, the subscript is the important thing. What does Q subscript 0 mean? It means that so far, there are 0 net favorable signals, positive signals, right? The number of positive and negative signals have canceled out so far, or the number of investments and non-investments have canceled out so far. So we are starting from that sort of position. So the Q0 is capturing, starting from that 0 position, what is the eventual probability that that an investment cascade will start, right? That's what Q0 is capturing. What is Q1? Q1 is basically the same probability. What's the probability that eventually an investment cascade will start? When we start with at 1, 1 is the net number of positive signals. Okay, so if we let's go back to 0. We are looking at Q0, right? So we start here. Now, with 4/5 probability, the next signal the next investor gets is a positive signal, because after all, the underlying state is 1, right? So that means he will invest. Everybody observing him will know that he got a positive signal. So that means that the net number of known positive signals will jump to 1. Okay, that accounts for this part. Now, with 1/5 probability, starting at 0, the new guy gets a negative signal. So then immediately he chooses non-investment, and immediately people know that the net number of positive signals out there is -1. Okay.
Yes, sir.
Now, the moment it goes to -1, a non-investment cascade starts, as I discussed at the very beginning.
Yes,
right?
sir. No.
That's why the probability of investment ever happening again drops to 0. Yes, all of these values of the everywhere here and everywhere there, a cascade has already already started. Sorry. So as long as the known number of net positive signals fluctuates between 0 and 1, the game is on. The game hasn't finished. Yes.
So whenever the game goes on to -1 or +2,
Or plus
these
2.
are
Yes,
observing states. Like these
absolutely.
are observed.
Yes.
Okay, sir. Thank you, sir.
Yeah. So this is the general technique of doing it when you have these asymmetries. So if you had different numbers, you could adopt the same approach and solve them. Yeah. Questions? No questions? Uh, um, okay, there's a number of questions in there on cheap talk games, right? Now, you will notice that in all these questions, I mean, there's a little twist. It's not exactly what you saw. I mean, that's the purpose, right? Whether you understood the logic and the reason of these models. Um, so if you don't try to memorize everything mechanically, obviously, right? If it's much easier when you remember the logic rather when you try to memorize formula and so on. So let's look at this number 9. All right. What was question number 9? Um, um, okay, yeah. Um, so it's a cheap talk game with 2 receivers, R1 and R2, and 1 sender, right? So there are 2 receivers, they'll each choose their own actions. Yes. And the sender wants to influence both their actions towards what he wants. Um, and instead of taking quadratic preferences, I've taken here uh, absolute difference, right? So he's trying to minimize not the squared error, but the absolute value of the error, right? What his bliss point is and what is the actual action. And as far as the 2 actions of the 2 receivers is concerned, he's adding up his payoffs, right? So the question says, consider 2 versions of the game, one in which there's private communication. So he has separate phone lines to the 2 different guys. And he can send them private messages. So he can potentially send a different message to each of them to manipulate them differently. Versus one where he makes a public announcement and both of them here, right? So all 3 are in a room and the sender sends a message which is heard by both. He cannot shield one from the message that he sends to the other. So public versus private communication. Which is better? That's the kind of thrust of the question. Now, when you have the private communication, each game is basically separate. So you find the partition equilibrium for each of the 2 games, right? And that we know how to do. I mean, we have done it for quadratic. You can easily do it for the absolute value. It'll basically be the same. You find that you have the same difference equation. So essentially identical. Now, public game, right? That's the twist that we haven't talked in class now. But then you have to sit down and think, right? What if it's publicly talking to these two guys. Now, let me pull up the solution. Yeah. Okay. You guys hear me, right? I haven't lost connection.
Yes, sir.
Okay. So now in the public message game, there'll be only one partition, right? It's a 3-player game. Now, how do we solve for it? Well, you have to remember the 2-player game. I mean, what was the critical thing? The critical thing was exploiting the indifference condition at the cutoff points. You have a partitional equilibrium. At every cutoff point, the speaker, the sender, has to be indifferent between sending the lower message versus the higher message. So we apply the same principle here, right? We exploit the same cutoff condition. It has to be modified because there are two listeners taking two different actions. That's the only thing. The logic is the same. So, so here's the right. So let's say so here's a cutoff. Okay. So we want to apply the indifference condition at this point, at this cutoff. Okay. And that means that, you know, there's this message mk plus 1 and this message mk. He has to be indifferent between these two messages. Now, when he sends the message mk plus 1, there's a higher action, which is a k plus 1, chosen by one of the receivers, right? And another action chosen by the other receiver. And similarly, when he sends this, there'll be two, not just one actions, right? One action coming from each receiver. One AK2. And earlier you were saying, you know, we were reasoning that, well, if there was only one receiver, then the two actions have to be equidistant from his bliss point. His bliss point being theta k plus whatever his bias is, b, right? Now the average of the two actions have to be equidistant from his bliss point. That's the new condition, right? So it's a bit more complicated, but the general reasoning is the same. So that's what we have here, right? And when you simplify that, you get basically this condition that yk plus 1, the interval of the length of the k plus 1th interval should be the kth interval plus some 4b prime. Now, what is 4b prime? 4b prime is the biases. So here we have normalized the sender's bias to be 0, right? And we have given biases to the two receivers. So B1 and B2. So B prime is the average bias of the two receivers. Okay. When we had only one receiver, we had exactly this. You have to incorporate the bias of that single receiver. Here you have to insert the average bias of the two receivers. That's what the indifference condition, when you work it out, that's what it gives you. Now, it has implications. Take an extreme case where the two biases are equal and opposite. Yes, then their average bias is 0. Okay. And when their average bias is 0, essentially all the intervals are going to be of equal length. In fact, you can create an equilibrium which is not even partitional, which is fully revealing. Yes, where and if you think about it, it's fairly intuitive because, you know, there are two guys listening to me. One of them chooses an action which is higher than what I want. Another chooses an action which is lower than what I want by equal amounts. Now, if I exaggerate, the guy who, you know, chooses excessively low actions, I'll be able to influence him and he'll choose higher actions closer to what I want. But the other guy who tends to overshoot relative to what I want, he'll go further away, right? And similarly, if I, instead of exaggerating the state of the world, if I underreport the state of the world, I'll pull one of them in the direction I want, but the other one will move further away, you know, and then I'll have a greater error as far as the choice of the other is concerned. So public speech, if, you know, the listeners are of different biases, and if I'm trying to influence them in different directions, then public speech acts as a discipline. Then you know, the fact that there are multiple stakeholders with interests in, you know, qualitatively different directions, that makes senders, speakers more honest. Yes. Okay, any other questions? Any questions on the last one? So again, the thing is, you have to keep your thinking hat on, right? And things are very simple if you do so. It's not hard at all. But you have to keep your thinking hat on. You have to rely on your understanding of the logic rather than formula and memorized stuff. As far as the essay type questions are concerned, you know, the answers which are written down, they are a little, perhaps slightly, you know, you can elaborate on them a little bit, but in a compact way, they are they show you how to answer. So you know, maybe the answer you should write should be slightly longer, maybe slightly more elaborate versions of these, but roughly along these lines. Any questions, guys? So Showmendo, is there, you're taking a session when, on Wednesday?
I will take a session tomorrow.
Tomorrow.
And if I have time, I will coordinate with these guys and try to take some other sessions also.
Okay. All right. All right. Okay, so as far as I'm concerned, I will be taking another final review session on Friday. Yeah, usual class time, 1:50.
Yes, sir.
Yes, and let me emphasize, you know, I'm just going to post the next lecture video on the reputation topic. Now, I'm pretty sure, I don't want to say it aloud, but I doubt whether you've been paying too much attention to the next topic because it's not in your syllabus. That's not what I'm recommending. You should you know, set aside an hour and a half to listen to that lecture. But in any case, I want you to listen to the two lecture videos on the reputation topic, which I've posted. Well, I've posted 2.5. Well, I will be posting 2.5. I've posted 1.5, and another one is going up soon. Basically, the two papers, one is Sharfstein and Stein, reputational herding. The other is Steve Morris, political correctness. And there's an introductory shorter video in the start. So make sure that you have listened to these videos before the class on next Monday of next week, right? So I just wanted to emphasize that. Up to you when and how you listen to them, but listen to them before next week's class. Okay, guys, if there are no further questions today, then I'll end it there and see you on Friday. Okay.